Okay, so the IBM hardware security module, which was there's a bunch of them, but the classic one was IBM 4758 that identified the hardware security module. That had a special key hierarchy, um, and very similar to the Visa security module. The idea being that you have hierarchies of keys. The very top level ones are the master keys that should never leave the crypto processor, that should stay inside the crypto processor once they're in. And then below that are maybe uh, less strong keys, I guess you could say. They're things like transport key. They're called transport keys, or in the IBM system, it was called key encryption keys that allow sharing between processors. These ovals are keys, and these might be keys, but they might be something else, and that was really the problem that we ran into. These rectangles represent types. So these types, remember, they could have keys, but they also imply some kind of access control. At the very lowest level, or I guess the very last two levels, are the operational keys and working or session keys that are used for most normal operations, and they can go outside the crypto processor. This key typing system assigns type information to the keys for fine-grained access control. So these type system, these rectangles, also imply some kind of access control. Who can access what? And these hardware security modules typically have two modes, like a supervisor mode and a regular user mode, things like that. And there were all these specific rules about what you could transfer by whom and things like that. IBM used this was what CCA stands for, the Common Cryptographic Architecture API. And the CCA name for key type that we used in Visa security modules is actually called, in CCA it's called control vector. So you'll see CV, whenever you see CV, you want to think of that as type or control vector. This kind of implementation was used in IBM across many products since 1992, and especially this concept of type. So if you encrypt something, using something like DES, this is what it'll look like. You would have a key, you would encrypt it using a master key and a control vector, and so you end up with an encrypted version of the key and also some type information, and that's what this whole thing represents. Okay, so one of the problems was with the function called key part import. So just like with the Visa security module, you might have three principals, each being a holder of one part of a key. So let's say KPA, KP, oops, that should be KPB, and then KPC. And then the final key K would be a combination of the exclusive OR of these three parts. And this key part import function, basically what it does is takes the imports each of these three parts and then does an exclusive OR of a chosen value with an encrypted key. So the reason for doing this, once again, as before with the Visa security module, was that all three must collude to find this K. But any one key part holder can choose the difference between a desired K and an actual value, and that turned out to be a vulnerability. So one attack is to perform an unauthorized typecasting, and that's what you're doing when you're taking a key and storing it into some other type. And this attack used IBM's pre-XOR typecasting method. And the details of this is really not important, but just to know that there was a vulnerability that allowed you to import a pin derivation key as a data key, pretty much just like in the Visa security module. So here it is, a little bit more of protocol notation, but not exactly. You would generate this key encryption key, first part using some original key, and then the second one using the original exclusive OR with these two types, the old type and the new type. The normal import process decrypts using this old CV. So if you take a look at this, you're decrypting It could just be a DES encryption. You're just doing the decryption step with this KEK1 exclusive ORed with the old control vector. Remember, control vector just means type, and so that implies access control. And so you're decrypting something that was encrypted using the exact same key, and that's how DES would work. They are symmetric encryption steps. And the thing that was encrypted was the key, and so when you decrypt it, you get the key back. The attack would involve claiming that the key was protected with KEK2 and bind it with a new control vector. So remember, control vectors imply access control, so you could put in any kind of access control that you could give people access to things that they shouldn't have. And so the attack was to decrypt using not this KEK1 but KEK2 with the new control vector, something that was encrypted using KEK1 and the old control vector, and that if you do things just right, you could work back and get the key. So why should you do this? Because you can, if you cast this key this way, you can actually change access control on keys and get access to things that you shouldn't be able to access. That's the general idea. So IBM had known about this attack and documented it, but it was obscurely documented and then completely forgot about it until the authors of the textbook and his friends figured out that you can do these. Okay, so those are, once again, problems with keys. There's protocol involved, and I guess we didn't really use a protocol notation, but this, once again, it's a problem of handling keys, key management. I mean, we'll wrap up in the next couple of videos, maybe just one more, and then we'll see one more maybe protocol at the end.